So now we're going to move into section 4.2, which is about exponential functions. So if you're not super comfortable with your properties of exponential functions, make sure you go back and look them up because we're going to utilize them pretty heavily. The one I do want to focus on predominantly, though, is that if you have a value a that is a real number, m is any integer, same thing with n being a positive integer, then if you have a to this fraction m over n, there's a couple of different ways you can go about rewriting this. So remember that 1 over n is going to represent a root. So you could take this as m to the 1 over n because you would multiply those. Or you can do the reverse. You can do a to the 1 over n to the mth power. And in that case, the 1 over n is that nth root. So an exponential function is going to be a function with a specific property. You have a base b, so the base is going to be a constant number. Your variable is going to be the exponent. So exponential functions are the form f of x equals b to the x. We want b and x to be any real numbers, but that base has to be greater than 0. And we're also really going to ignore the case when the base is equal to 1 because it would be really boring. I'm going to show you it in just some graphing examples, but most of the time it's going to be something other than 1. It's 1 to the x will just be a constant function 1. So let's look at two just short examples. I've got a function 3 to the x, and then I have x to the third. So they're very similar in looks to each other, but that location of the variable is important. So this first one is an exponential function with base 3, while when your variable is the base, that's a power function. So exponential will always have the variable in the exponent. Power, you have a constant power. So that's our main difference between these two. So let's go ahead and work with an exponential function. For f of x equals 4 to the x, we're going to evaluate the following. So the first thing we're going to do is we're going to find that function evaluated at -1. So anywhere I see an x, it gets replaced by -1. And then our properties of exponents tell us if you have a negative exponent, it moves in the denominator. So this function evaluated at -1 will have an output of 1/4. If we want to evaluate it at 3, that's just going to be 4 to the third power, which is 64. And then if I want to evaluate this fraction or this exponential function to a fraction, that's 4 to the 3/2, you can break this apart in two different ways. It's probably going to be easier to work with that root first. So I'm going to do 4 to the 1/2, and then I'll raise it to the third power. It's 4 to the 1/2 is the square root of 4. That's 2. And then I will raise it to the third power. So you get 8. You could do the other way and do 4 cubed and then take the square root, but sometimes if you have a high number, it's going to be easier to do that radical first. Now, based on the value of the base, we're going to have technically 3 different appearances of the graph, but just 2 of them are going to be the important ones. So based on the value of the base, it being between 0 and 1, it being exactly 1 or greater than 1, we'll have a couple different options for the graph. When the base is equal to 1, that is the most boring case because it's just going to be a straight line, which is why we're going to ignore this one most of the time. And in this case, your domain is anything you want, but your range is just going to be 1, so it's boring. In the case you have a base bigger than 1, if you have a very large value, say 4 to the x, you take 4 and raise it to the 100th power, it's going to be huge. If you take 4 and raise it to the -100th power, that will move it in the denominator and it becomes a very small fraction. If you have 4 to the 0, you're going to go through that point 0, 1. So in this instance, your graph of the exponential function will have this appearance. When you have a base between 0 and 1, same type of thing happens because if you plug in x is 0, you're still going to go through 1, but now it's going to be a flip graph. So if you think 1/2 to the 100th power is a very small number, 1/2 to the -100th flips that fraction and becomes 2 to the 100th. So you're going to have this reverse effect. So here, one thing you want to notice about these two particular graphs is they're really just reflections of each other about the y-axis. So that's a nice thing about these two. And then properties for all of our exponential functions, excluding that one weird case, we have the same type of domain, range, and asymptotes that go on. So the first thing is for your exponential function with base greater than 0 other than 1, your domain is anything you want. You can input whatever you want. The range, however, is going to be from 0 to infinity. You're not going to be able to equal 0 either. There is a horizontal asymptote because you're going to get very close to hugging that x-axis. So your horizontal asymptote occurs at y equals 0. In both of these cases, you're not going to cross the x-axis, so there's no x-intercept. If you do start shifting this around, then you can have an x-intercept, but for the basic graph, there's none. And for the y-intercept, when you plug in 0, regardless of that base, the output will be 1. Now we do have a very special base, which is called our natural base. So you probably have dealt with pi before, you've probably seen e before, but this is going to be our natural base. So e is an irrational number that occurs in many realistic applications. It is a number, it is about 2.718, it's got a bunch more values after, it continues on forever, but it is going to be an important base for us. Another way this thing actually comes about, it's the value that 1 plus 1 over n to the nth power approaches as n gets larger and larger. So it goes to infinity. So because this is an important base, we do want to know that graph of it, but it's the same as an exponential function with base bigger than 1. So e to the x is going to have the same basic shape that this graph does. It will continue to grow forever. So now let's go ahead and let's apply some transformations, and let's go ahead and graph f of x equals 2 minus e to the negative x. So we've got two transformations that are going on. I've got this minus sign out front of the e to the x, so that's going to tell me to reflect my graph about the x-axis. And then the second transformation we have is this 2 out front. And that's going to tell us to shift the graph up 2 units. So going back to our stuff from chapter 2, you've got to make sure that you apply that in the appropriate order. I don't have a horizontal shift, but I do have this reflection. So the first thing I want to do is I want to reflect y equals e to the x about the x-axis. So if we look at our graph of e to the x, we know it's going to go through 0, 1, and e to the x will grow like this. We have a horizontal asymptote, and that's going to be right here on the x-axis. So y equals 0 is our horizontal asymptote. So when we go ahead and reflect it, the point 0, 1 gets reflected to 0, negative 1. And here would be our graph of y equals negative e to the x. Now I want to take this and I want to go ahead and shift it up 2 units. So we've got our graph here, which I'm going to sketch in. Here's y equals negative e to the x. My horizontal asymptote didn't change because when you do that reflection, it doesn't change anything. So for negative e to the negative x, y equals 0 is the horizontal asymptote. Now we go ahead and shift it up 2 units. So that's going to also shift our horizontal asymptote. So y equals 2 becomes the new one. Now I have to shift these points up. So we're starting here at 0, negative 1. It goes up 1, 2, and will land us at 1. And your graph will still keep the same basic shape. So here's y equals 2 minus e to the x. And if we want our properties, our domain doesn't change at all. It's negative infinity to infinity. Looking at the range, I can go up to that horizontal asymptote, but not include it. So it's from negative infinity to positive 2. And your horizontal asymptote is the line y equals 2. Okay? So the really nice thing about these exponential functions is they appear a lot of times in population growth and also in financial calculations. So we're typically just going to focus on the financial applications, but you can talk about a lot of populations like rabbits. Rabbits double pretty quickly because they're constantly giving birth to new babies. So you can model that with an exponential function. But we're just going to focus on two types of financial applications, the first one being compound interest. So suppose you invest a certain amount of money in an account and it's going to compound interest n times a year. So a lot of banks will compound your interest monthly. Once a month, whatever amount you have in that account, it's going to calculate interest based off of that. So if you get a 3% interest rate for the year, it's going to split that up over a bunch of different payment options. So it's not 3% each month, it's 3% over the year. So the amount of money in the account can be found by using this formula. You have A, which is the amount, is equal to P. So you get the initial amount you vested times 1. You have to take your rate and divide it by the number of times it's getting compounded. So this tells you how much it's going to compound each time. And then it gets raised to the NT. So what do each of these pieces represent? A is the amount of money at time T. P is what we call the principal, which you can think of as your initial investment. T is the amount of time the money is invested. So that's going to be in years. R is your interest rate, but you want to make sure it's a decimal. And then finally, N is going to be the number of times the interest is compounded each year. So let's look at an example. We want to figure out how much money should we put in a savings account now that earns 3% interest a year, compounded weekly, if we want to have $80,000 in savings after 15 years. My goal is to figure out what I need to invest, which is my principal. So this is my unknown. Now I need to figure out what all my other pieces are. My rate is 3%. So as a decimal, that's 0.03. My time is 15 years. The number of times it gets compounded is 52 because it gets compounded weekly. There's 52 weeks in a year. And then the amount I want in my account is $80,000. So I want to plug all of these pieces into my formula, figure out what P is equal to. So we get 80,000 is equal to P times 1 plus my rate over N to the NT. So we got to figure out what the value of P is. So if you take 52 and times it by 15, you're going to get 1 plus 0.03 over 52 to the 780. If you go ahead and plug this into your calculator, you're going to see it's about 1.5681. So to solve for P, you just divide by this constant, and it gives you a rough estimate that P is $51,016.87. So really, we should invest this amount to guarantee in 15 years, we're going to have $80,000. So these accounts are nice. It's going to be hard to find an account that would actually give you 52 times compounded interest. An even better type of account is something that's called continually compounded interest. So you can compound it monthly, which is most common, weekly, daily, and in the limiting case, it's going to be continuously. So basically your balance is going to grow by a small amount every single instance. And in this case, if we want to determine our balance, we're going to use this other formula, A equals PERT. So a lot of people remember it as A per. So if you really look back at this limiting value, you've got 1 plus 1 over n to the n. Remember, as n goes to infinity, this goes to e. So that's where that compounded interest turns into the continually compounded interest. So everything still has the same interpretation. A is the amount after t years. P is your initial investment. R is your rate, which is a decimal. and t is the time in years. So same still meanings of each of the variables. So let's try one last example. Let's find the future value and interest earned if $8,906.54 is invested for 9 years in an account earning 4.5% interest compounded continuously. So we need to find two things. We need to find the future value. So that's basically what is the account going to look like? And then the interest earned. So I have to figure out what's the difference between the two. So my principal is that initial investment. It's the $8,906.54. My time is 9 years. And then my rate is 4.5%. So as a decimal, that's 0.045. So we go ahead and plug this into our formula. A is equal to P, E to the RT. So exactly, that's going to be $8,906.54, E to the 0.405. And if you plug this into your calculator, it'll be about $13,353.60. So our future value is exactly this. That's how much is in our account in the future. The interest earned is I have to take my future value and I have to subtract how much I actually put in the account. So it gained $4,447.06.